Hey everybody, my name is Jacob and this is Archimedes Tab. Today we're going to be discussing measures of variability. So, if you see my last video where we talked about measures of central tendency, we learned about stuff such as the mean and the median. But something to note is that these measures of central tendency are not sufficient to describe a data set by themselves. This is due to the fact that we have different data sets that can have very similar means and medians to each other. Fortunately, we can use variability to further our understanding of individual data sets. One of the most well-known measures of variability is the range, denoted by R. So range is simply the largest observation of a data set minus the smallest observation in that data set, which follows the formula R is equal to X max minus X min. Unfortunately, the range is not actually an adequate measurement of variability in a data set because it can be strongly affected by outliers. Graphing is a good place to start when trying to get a sense of the spread of a data set. Let's look at an example of two different data sets that have similar means and medians. To do this, we're going to be utilizing a software called RStudio, which I've covered in a previous video. And RStudio is basically a GUI for the R programming language. So let's get into that. So the first thing we'll start with is generating our random data sets that have similar means and medians. And we'll use this code here, set.seed, with the digit 1, 2, 3 in there for our reproducibility. And we can actually show you what that function does. Over here by typing set.seed into the console and then hitting Control Enter. And that gives us this pop-up in the Help tab over here, which describes generating a random seed. So you can pause the video and read that if you would like to, or just type in set.seed in the RStudio console and with a question mark before it and hit Control Enter and see for yourself. So we'll get on with generating our data set. So we will highlight this here first, hit Control Enter. Alternatively, you could have just clicked your cursor at the end and also hit Control Enter, or this Run button at the top of the coding window there. So after we create our seed, we're going to go to this line of code here, which generates the vector x1, which is going to contain 30 variables with a mean of 10 and a standard deviation of 2. So we'll go ahead and generate that by clicking at the end of the line and hitting Control Enter. And you'll see over here in our environment window that we have this object here named x1, and you can see it's numeric with a length of 30 different observations. And here it lists some of them, but we can also go to the console window. And if we want to view that vector of numbers, we can type x1 into the console, hit enter, and there it gives us a list of all the values of x1. We'll go ahead and clear that console window by hitting Control L. Go back up to the coding window here. And from there we'll generate a stem and leaf plot that shows the distribution for the first data set. And we use the stem function that comes with the base R programming language, and the arguments we pass to it are our data, which is the x1 object vector with a scale of 1.5, and if we hit enter, it'll show us this stem and leaf plot here in the console window, and that gives us an idea of the distribution of that particular data set. And you may be wondering why the scale equals 1.5 up there. Well, I'll change that, or simply remove it, to show you what exactly that does. So go up there, remove that, hit Control Enter, and we'll go look back down at the console window. And instead of this here, I'll actually pull this up some so you can see both of them. You can see that I guess it didn't generate a different stem leaf plot. Interesting. Not sure why I had that stem or the 1.5 thing in there. That must have just been for me goofing around with the thing, with the code. Let's actually clear that, and we can actually look at the arguments of the stem function and see what scale does. So we'll go over here to our help window, and we can see that scale controls the plot length. Okay, that explains why it didn't do anything. I must have just been messing around with a different data set. Anywho, alright, so after that, we'll go ahead and generate our second random data set that is similar to the first data set. Click that, go to that line, click Control Enter. You'll see in the environment window, we now have the x2 object, and we can scroll over, see it's numeric, also contains 30 numbers, and assume this is there, and we'll go down here to the console window, clear that out, hit x2, and that displays all of our numbers for that particular vector there. Clear that out. All right. All right, so let's compare the stem and leaf plots for x1 and x2. That's the one for x1. It's the one for x2. Now you can see that they have similar distributions. Okay, so I know why I had the scale equals 1.5. The data set, I've generated multiple random data sets working on this video, and I believe if I go in and type scale equals 1.5, it'll fix that gap there, and that can be used to like help determine whether something is actually an outlier or not, playing with your scale and for histograms or bin values and such. So bring that down. Not that far though. One second here, having technical difficulty. There we go. Okay. So let's do that scale function. Now x2 scale equal to 1.5. Now let's run that. That did not fix the thing there. Anywho, well, we won't continue to worry about that. We'll just focus on the topic at hand, which is measures of variability. Anywho, alright, so now we're going to compare the mean and median values of the two data sets. And what I'm actually going to do, let me fix that to show both. Change that to x1. X1. Alright, we'll highlight and run that. We can look down at our console window here. And we see that the mean and the median are both around 10 for the x1 data set, and then for x1 or for x2 data set, we can look at the mean and median for that and see that they're both in the range of 10, pretty close together. So what we're looking at here is two data sets with means and medians that are incredibly similar, even though the data sets are entirely different. So let's hop back over to the whiteboard. So now we're going to talk about determining the ith deviation about the mean. So in a numerical data set, the ith deviation about the mean is determined by the formula xi, where I represents a specific value in the data set. It just the number of an observation could be observation 5, 9, 11, 10, whatever, minus x bar, which if you remember from my previous videos, which means the average of the data set denoted x. And to give an example, the third deviation about the mean would be calculated by the formula x3, with 3 being the third value in the data set, minus x bar. Now, to find a suitable measure of variability, all of the deviations about the mean will be considered. Something we will realize is that the sum of all observations about the mean will be equal to 0. This is because the positive deviations of the negative deviations cancel each other out. One way to deal with this is to instead sum the absolute values of all the deviations. A small sum indicates a small spread, while a large sum indicates greater variability. However, there is a way to make all of the deviations positive as well as better reflect the variability of the data set. We can do this by calculating the sample variance, denoted s squared. This is calculated by summing the squared deviations about the mean and then dividing them by n minus 1, and we have the formula for that. S squared equals 1 over n minus 1, n minus 1 representing your degrees of freedom, multiplied by the sum of x at the ith deviation minus x bar squared. And S squared is a measure of variability, so it is useful for comparing data sets. From there, you can calculate the sample standard deviations, denoted S, by taking the square root of S squared. Finally, there's the quartiles of the data set. In any given order numerical data set, there will be 4 quartiles that the data can be divided into. Q1, which is the median of the bottom half of the data set. Q2, which is the median of the data set, aka the 50th percentile, aka x with a tilde over it. and then Q3 is the median of the upper half of the data set. And then finally, you have the IQR, or the interquartile range, which is equal to Q3 quartile 3 minus quartile 1. Now, usually you're going to use software to figure out all these values. Like, for example, in RStudio, we can simply type into, we'll go to the console window here. We can type in summary x1, which was the first data set we generated, hit enter, and it'll give us our minimum. The first quartile, the median, aka quartile 2, aka the 50th percentile, the mean, the third quartile, and the maximum. This is our 5-number summary, which I probably covered in an earlier video. So we'll hop back over to our whiteboard. Finally, now there is a formula for determining your quartiles, but I frankly don't like to use it because you can do it with a computer just as easily. So basically, if you wanted to find quartile 1, you would say D, which is for depth, which means like depth as in position in the data set. Because it's an ordered data set, you would say D1 is equal to N divided by 4, and N is equal to your number of sample observations. And if you want to find the third quartile, it would be D3 is equal to N3 over 4. So, and there's a rule for that. If your depth number is a whole number, then your depth is D1 plus 0.5. So, and if for D3, same thing. And for D1 and D3, if it's not a whole number, you round up to the next whole number for the depth of Q1. If you like this video, be sure to like and subscribe, hit the bell if you want to, give us a thumbs up and all that. We do have a Patreon and a GoFundMe if you want to check those out. Links will be in the descriptions below. We appreciate all the support we can get, and we've got a lot of interesting stuff that we're going to be coming out with soon. That's not specifically statistics related, mainly chemistry stuff. But if you're interested in that and you want to see that, be sure to like, subscribe, hit the bell, and you'll see when we upload it. Thank you guys.
Hermit crab mimicry. I carry my shell with me, so if the wind lifts me, I'm home despite the shifting. Sifting simply through the sands of time, my mind, an hourglass itself, grew hands to manifest the rhyme before I'm back upon the shelf. So if you feel a similar, familiar sensation, substitute the simian for crustacean dedication. Clap your hands or better, click your claws. The laws inside the nation contain implicit clause, explicit force, extermination. Some defend with venom, while some prefer evasion. Some live in the plenum, but others isolation. Regardless of the habitat, the cataract exists. Consume the womb, a savage act to fill the hollow pit. The rift exposed remains opposed to logic, not to gossip. Dragged down by the undertow, where the bottom feeders frolic. Build your castle made of sand with no plan for support structure. Just don't hassle me with your hand out when the walls fall and crumble.